Hi, in this video we are going to talk about chemical bonding and the types of bonds and what forces or causes specific types of bonds to occur. As you probably already learned, this is a representation or a model of an atom called a Bohr model. Remember, it's inaccurate as to what the behavior electrons actually are doing, but it's useful in describing how the atom will behave due to the electron shell, the valence shell that's out here. So remember that a bonding or a bond is that force that's going to link two atoms together. And of course, you can have way more than two atoms linked together in a molecule, but just the bond itself is at least between two differing, or maybe of the same type, but two individual atoms that are going to be linked together somehow. So again, it is the valence electrons here, the outer shell electrons, that are really going to determine how it's going to behave. We're not talking about behavior as in some sort of conscious decision, but whether or not an atom is going to enter a bonding relationship with another atom to form a molecule. So remember the octet rule. The octet rule states that besides the first energy level or electron shell, which is going to have two electrons in it, the next outer rings for most of the organic compounds we're talking about and the atoms involved there are going to have 8, or they are going to like 8 or want to fulfill 8. So really, how do the atoms behave, or whether or not they're going to have or form a bond with another atom, is going to be determined by the electrons in the valence shell. And it, again, has to do with the octet rule. That octet rule is how can we get to 8 or fulfill 8 electrons in the outer shell. So on the left here we have a sulfur atom, and if you look at the valence shell, there's 6 electrons. So it's 2 away from the octet rule, and of course the magnesium has 2. So how's it going to behave? And if you think about it, kind of just roughly thinking about what's the easiest path to fulfilling the octet rule, well, the sulfur atom is going to look for an additional 2 to gain 2, and the magnesium would look like losing 2. So it would want to get to the octet rule by losing those 2 electrons. Just to put this in some context of the periodic chart and how elements or how atoms of elements are organized into the periodic chart, the elements in the same row are going to have the same number of shells. So this has 2 shells. The inner shell, of course, has only 2 electrons in it, and then the outer shell is going to begin to fill up. Well, the next row down, the third row of the periodic chart, is going to have 3 energy shells. 2 electrons in the first energy shell, 8 electrons in the second energy shell, and then we'll start to begin to fill the outer shell. Moving from left to right, each element is going to have an addition of a proton and an electron. So at this point, when we have an idea of what's going on with the outer energy shell or the valence electrons in any given atom, we can introduce what's called electronegativity. So basically, electronegativity is dealing with the attractive force that a nucleus has on its electrons. So how electronegative an atom is how tight it pulls those electrons in. Now remember, a proton has a positive force, an electron has a negative charge. Therefore, the electrons are pulled in by the nucleus. So if we look at electronegativities, they're going to help us predict whether a molecule will be polar or nonpolar. So we're now talking about atoms of specific elements that enter into bonding relationships with other atoms. They may be of the exact same type. For example, oxygen may bond with another oxygen to form an oxygen molecule, right? But you may also have a hydrogen atom bond with oxygen atoms in order to form, say, water. So we're going to be able to predict whether we have a polar or a nonpolar molecule. So So before even discussing the types of bonds that there are, let's continue on with electronegativity for a second, because electronegativity really governs the attractive force between the nucleus and electrons. So there's simple charts that can show us this, but if we look at the periodic chart, we also know that as we go from left to right, we increase in electronegativity strength, and as we go from the bottom to the top, we increase in electronegative strength. So really, fluorine actually has the strongest electronegativity, and what it's talking about is, remember that the electrons don't really contribute anything to the mass of an atom. They are relatively so tiny that they really don't, their mass is negligible. We almost just call it as zero. But the protons have everything to do with mass. Every time you add a proton, the mass of the atom or element gets stronger and stronger. So with 9 protons, it really has a huge attractive strength. So it's actually going to pull in those electrons really, really tightly. Now, when we start talking about how other atoms are going to enter into a bonding relationship, we can look at how likely they're going to be attracted and how heavily the electrons are going to be attracted to the nucleus. So carbon actually has a relatively weak electronegativity, kind of like hydrogen. So it's going to, when it bonds with other compounds, it's going to likely form a nonpolar bond. And we'll get to those, to polar and nonpolar bonds, in just a second.
An atom attempts to attract electrons toward itself when bonding with another atom. The level of attraction of each atom is called its electronegativity. When sodium and chlorine react, the chlorine atom removes sodium's valence electron and becomes a chloride ion. The less electronegative sodium atom cannot compete for electrons and becomes a sodium ion. The attraction between the ions is an ionic bond. When bonding atoms have nearly equal electronegativities, neither can attract electrons away from the other. In a carbon-sulfur bond, the electron pair is shared almost equally between the two atoms, resulting in a covalent bond. When hydrogen and oxygen react, the more electronegative oxygen atom cannot completely remove an electron from hydrogen. The shared electrons are attracted more to the oxygen than to the hydrogen atom. This unequal sharing is called a polar covalent bond. Polar bonds have a slightly negative and a slightly positive end.
So back to the basics. We'll integrate this in a second, but back to the basics of chemical bonding, the atoms are going to tend to either completely fill a shell or empty a partially filled shell. Either way, they're going to want to try to fulfill the octet rule. So there's different types of bonds in biology, and we're going to look at some of these in a little bit more closer detail in a second. So the first type of bond to talk about are the covalent bonds. Covalent bonds, co meaning together. Covalent bonds are where atoms are shared between two different atoms. They can be atoms of the same type, or they can be atoms of different types. But they're very stable. Both atoms are holding on to the electrons and counting them as kind of as their own. So we've got hydrogen gas here. Well, H2. Well, an H atom or a hydrogen atom all by itself has 1 proton and 1 electron. But the innermost electron shell or energy shell is 2. Well, for hydrogen, it wants to have 2 electrons in its valence shell. By sharing or entering a bonding relationship, they both get to count the 2 electrons, and they both are satisfying. Although it's not 8 here, they're still satisfying the octet rule for their outer energy shell. So the 2 atoms share them. The thing is they may or may not share them equally, and that is determined by their electronegativity. There can be multiple covalent bonds and they can share more than one pair of electrons. So we can actually have double or triple bonds. Covalent bonds are very strong. The more you have, the better, and the more strong that bond is, the more difficult it is to break in a chemical reaction. So a nonpolar covalent bond, nonpolar, if you think about this, there is no charge on either end or on any pole of the atom or the molecule here. So the pair of electrons are shared equally by two different atoms. So the example here is hydrocarbons. Hydrocarbons. Hydro, they've got a hydrogen and there's carbon. This thing is the simplest hydrocarbon that there is, called methane. It's CH4. There's a carbon atom that has 4 hydrogens that are bonded to it. And each of the electrons are shared equally. What that means is that the nucleus of the hydrogen, or excuse me, of the carbon, is not pulling in the electrons any tighter than the nucleus of the hydrogen is pulling in the electrons. So there's a tug of war that exists because of electronegativity, which we'll review more, but essentially here, neither of the nuclei are winning, not the carbon and not the hydrogen. Polar covalent bonds are formed when atoms still are going to share the electrons in a bonding relationship, but they aren't going to share them equally. And why don't they share them equally? Because of what we learned about electronegativity. The attractive force between the protons in the nucleus of one atom and the electrons that are around them, their own and the electrons that are around them that they are sharing in the covalent bond. So the example here is water, and this is a perfect little example in a diagram of electronegativity in action here. So here, oxygen has a higher electronegativity than hydrogen. You know that from both the periodic chart, the rules of the periodic chart, but you also know it just from a electronegativity chart. But the protons of the oxygen atom, they win the tug of war. So both the oxygen nucleus and the hydrogen nucleus, they're both playing tug of war with the electrons. But who's going to win the battle? There's many more protons in the oxygen nucleus than there are in the hydrogen nucleus. Therefore, they're going to be pulled slightly farther in towards the nucleus of the oxygen than they are being pulled in towards the nucleus of the hydrogen. Therefore, the water molecule, the hydrogens are sucked in tighter to the oxygen, and that's going to form a slightly charged molecule. We refer to this as delta negative and delta positive. So this is because they're pulling in electrons closer to this end, this is delta negative. Because the electrons are being pulled in this direction, the hydrogens are actually delta positive. I want you to remember this concept or remember this characteristic of water molecules. Water is a polar molecule, meaning they are opposing charges on two different sides of that molecule. They are separated, positive versus negative poles, delta negative and delta positive. This leads to a bunch of interesting properties that we are going to learn about with water, and you should probably understand intuitively that water is a pretty important substance, and we're going to look at all of those properties in more detail in the future. Hydrogen bonding occurs between two different molecules. Hydrogen bonding is not what creates molecules from atoms. Hydrogen bonding occurs between different molecules. It can occur between different small subunits of molecules in really large molecules that are called macromolecules, but they're much, much weaker than the covalent bonds that form molecules, and they have a considerable role in maintaining the shape of great big molecules like proteins and nucleic acids and carbohydrates, etc. So the hydrogen bonding occurs because remember that water is polar. The attraction between the positive end of the hydrogens and the negative ends in the oxygen are going to make water very sticky. Remember that, and we will come back to it. So all of the additive effects of hydrogen bonds can be really, really strong in a substance, even though for an individual bond, it's a weak attraction. A different type of bond, which isn't as strong as covalent bonds, where atoms share the electrons in the valence shells, ionic bonds form between ions. Now, ions are special. Ions are changed atoms. They're charged, and the reason that they are charged is in order to fulfill the octet rule, ions actually gain or lose electrons. So this is really crudely put, but if an atom has one valence electron, it may just give that up. Well, now it's got an extra positive charge, so it's going to become a positively charged ion. A negatively charged ion is when it gains electrons, therefore it's going to have a slightly negative now charge. Ionic bonds are what are formed between two ions that are electrically attracted to one another. So as I already said, a sodium ion is going to have this extra electron in its valence shell. Because the chlorine atom needs one, it's going to actually donate its electron to the chlorine atom and make it into a chloride ion. Now the sodium has gone from being a sodium atom to a sodium ion, and it's become positively charged. Why? It lost one of its electrons that was balancing out the charges between the protons and the electrons. The chlorine atom has become a chloride ion because it's gained one of the electrons to fulfill the octet rule. Now, a lot of that is a little more than we need to know. What you really need to know, you don't really need to know which atoms are going to form which ions, but just know exactly how they're formed. So ionic attractions are actually weaker than covalent bonds. And so these salts, or ionic compounds, they dissolve really easily in water. And think about this for a second. We'll go further into this, but why would they dissolve easily in water? Remember that water molecules are actually charged. They have a slight charge. Why? Because they are polar. So the delta negative region of a water molecule is going to surround the cations, and the delta positive portion of the water molecules are going to tend to surround the anion, and they can easily dissolve those substances in water. More on that as we talk more about the water molecule. So we talked about the different types of bonds that exist, specifically covalent versus ionic bonds, and spent most of the time talking about covalent because there are polar bonds, polar covalent bonds, and then there are nonpolar, where there is no charge because of the electron attraction between protons and negatives is equal. So we're going to spend more time talking about bonding in the future, specifically with water, and I hope we learned something about bonding.